Okay, for our next lesson, we're going to talk about limits and how we can use those and discuss continuity. So the first thing that we have is going to be a definition of continuity. So when we talk about this definition of continuity, we're talking about being continuous at a given value. So we may have a function that's continuous over an infinite amount of values, but can still be discontinuous at a particular point. So the first part of our definition, and these three steps need to be memorized. The first one, does f at c at that particular value is defined? In other words, do we have a for sure value for that? That's our first step. The next step, we need to see if the limit as x approaches c of the function exists. So again, we're looking for a defined value. We're looking to see if the limit exists. And then the third and final thing is if the limit as x approaches c of the function exists, is it equal to the actual function's value? And if we can prove that those three things are true, then we can prove that we are continuous at a particular value. So keep these three steps in mind as we go through in a chart. So our next thing, for our very first part of this, we need to see whether or not a function has a value at the given x value. So what that means is we're going to look to see, do we have some for sure values here? So starting out at x equals 9, we're wanting to know, well, do I have a for sure value when x is 9? So if we look over at 9, we go over to x being 9, and we move up. Notice that we're a little bit between 3 and 4. So the given value here, the function's value when x is 9, is 3.5, something like that. And then let's look at when x is 4. Well, when x is 4, the given value, we don't have one. There's an asymptote there. So we're going to say does not exist. Okay, when x is 3, let's see, do we have a for sure value when x is 3? Sure, it looks like it's going to be 9. What about when x is 0? When x is 0, y is 6, or the function's value is 6. At negative 3, it looks like here our for sure value is down here. Now we want to look up here, and we would if we were talking about a limit value, but here we're talking about a for sure value, so we are looking down at the closed point, which is going to be negative 6. And when x equals negative 5, it looks like, let's see, when x is negative 5, we're going to have a value of negative 2. So all of those, we are looking for those closed circles or for sure values on the function. Okay, now let's look at the left-hand limit. So on all of these, we're going to look for the limit as x is approaching each one of these x values, but we're just looking at it from the left. So when x is 9, so we're looking at the limit as x approaches 9 from the left. So if we do that, if we're looking from the left as x is approaching 9, it looks like we're going to get 3.5. What about the limit as x approaches 4 from the left? Well, approaching 4 from the left, that one doesn't look like it's going to exist, so does not exist. Okay, what about 3 from the left? We're approaching 3 from the left. It looks like we're going to get 9. The next value should be 6. X is approaching negative 3 from the left. So negative 3 from the left, that looks like that might be 5. And then finally, looks like the last one, we're going to be at negative 2. Now we're going to approach that same number from the other direction. So we're going to come in from the right side. And if we come in from the right side, let's see, we're approaching 9. and we're coming in from the right side. However, the graph stops right here. And we can't make up stuff to the right of it, so that one does not exist. There's no graph over there. Okay, as we approach 4 from the right, then if we're approaching 4 from the right, it looks like we're moving upward. So that one is going to be positive infinity. For 3, let's see, we're approaching from the right of 3. Well, there's no graph there, so that one does not exist. At 0, looks like we're going to get, from the right, we're going to get 6. X is approaching -3 from the right, so let's find -3 from the right. It looks like it's going to be 5. And then finally, the last one, it looks like it's going to be 7. Now let's generalize this, just the general limit. So we're looking to see, does that actual limit exist? So let's see, does the limit exist at 9? Well, from the left and right, this column and this column don't equal each other, so the answer here is does not exist. What about on 4? Nope, those two, so does not exist, does not exist. Oh my. Oh, down here it does exist. It's going to be at 6. And from the left and right, let's see, this next one, it does. The limit is 5. And then the last one, let's see, from the left and right, does not exist. So now we can make some conclusions about our actual limit value. And we're saying that because you can look at this from the actual value. This was step 1 in our chart that we put. Does f at c exist? Here. The next one we're looking to see, does the limit as x approaches c of f of x exist? So we're looking at that. And then finally we're looking to see, do those two equal each other? So let's look at the very first one. The answer would be no, we're not continuous at 9. And graphically we see that. But here we're not always going to have the graph, so we need to rely on the algebra as well. So at 4, no, that was an asymptote. Let's see, at 3, are we continuous at 3? Well, no. But here at x equals 0, and we can see graphically at x equals 0, we are continuous there. So the answer here is yes, and then the remaining ones would be no. And here is a great statement to help us put all this together. Limits, that was the intended value. That's where we're headed toward, the intended value. Continuity guarantees that we actually got to that value. So that's the difference in the two. All right, let's move on to some other problems. Now we're going to talk about, since we've figured out whether or not we're continuous or not at a particular point, then we need to classify those types of discontinuities. So classifying those, notice that the first one, and y'all have heard me say in class that a hole is a removable point of discontinuity. And we've talked about that happens here. That's removable. That's coming from where we factor and cancel. We're making those holes in the graph. So that's something to keep in mind. Now when we had a jump, that's a one-sided limit exists, but the actual limit itself doesn't exist. So in other words, here we can look for a limit coming in towards x from the left, and we can look at it from the right, but the actual limit itself does not exist. And the same is true on this one here and here. So again, that's going to be just where your one-sided limits exist, but they don't equal each other. Now over here on this last one, that infinite, a lot of times people associate that with a vertical asymptote. Because notice here there would be a vertical asymptote, but now not always. Here's another great example how you don't necessarily have that. You've got an existing point there, but everywhere else you would not be existing along through there. So those are things just to keep in mind. Over here, they want us to classify the type of discontinuity, and they've given us the graph to go with the particular function. And so this first function, A, is called a step function, and that's not something you see a tremendous amount of, but let's go ahead, just in case it pops up. This is called a step function. And you see this more whenever you're talking in business finances. This is going to be a step function. Maybe when you talk about different kinds of interest rates and such. This is a non-removable discontinuity. Well, my pen stopped. Okay, so step function, it's a non-removable discontinuity. And notice that you're not always going to exist. It's almost very one-sided here. Okay, so there's a non-removable discontinuity. You could also think about graphs that have vertical asymptotes. Another example. All right, and then over here at part B, this would be a non-removable as well. There's nothing that you can really factor and cancel out, but it is also, notice there's a jump here to get from one to the other. So this is a non-removable discontinuity. Okay. Now, look at what the non-removable discontinuity, the limit as x approaches, let's see, what value do we have in question 3? The limit as x approaches 3 from the left of g of x, well, that's going to exist. That's going to be at -1. And then the limit as x approaches 3 from the right of g of x, that's going to be +1. So notice the one-sided limits exist, but the actual limit itself, as x approaches 3 of g of x, that does not exist. So do keep that in mind. All right, so let's jump into some of these problems. And we're trying to decide whether or not we're continuous. And we can look at the graph and figure out whether or not we're continuous. But we need practice with our particular steps. So for the first thing we're going to talk about is, do I have a value for f at 1? And I do have a value for f at 1. It's sitting right there. And it is 3. Well, let's look at the next one. Let's talk about the limits. So I need to know the limit as x approaches 3 from the left of our function. Does that equal the limit as x approaches 3 from the right of the function? Well, let's see. The limit as x approaches 3 from the left, as x approaches 1, my crack's wearing off. All right, so as I approach 1 from the left side, it looks like we're going to get 1. And that's definitely not equal to 3, so our limit does not exist. So here we would have that the limit as x approaches 1 of our function does not exist. Okay, so here that limit doesn't exist, and so I see that if the limit doesn't exist, then there's no way for us to be continuous. Now let's think about this. Our one-sided limits did exist, but we were not continuous there. So here we're going to say we're not continuous, and really we have a jump discontinuity. We could go ahead and classify that. All right, so let's talk about the next one. And again, we see here, if we just start off at 1, well, f at 1 does not exist. And if it's not defined there, there's no way we can be continuous there. So, and notice that our limit does exist, but again, just because that limit exists does not mean that we're continuous here. So, and notice that this is just going to be a point of discontinuity because it's a removable point. So this is a point of discontinuity. Looks like we were able to factor and cancel. All right, so let's look at this last one. So here it looks like in question would be 1. So let's see, is f at 1 defined? And it is. F at 1 is 2. So now let's look at the limit. As x approaches 1 of our function, and notice that that limit, as we come in from the left and from the right, both of those sides are approaching 2. So finally, our third step, we need to see if the limit as x approaches 1 of our function, is that actually equal to f at 1? And the answer is yes. We have 2 equals 2. So here we are continuous at x equals 1. Okay, for the next part, we are told not to graph this, and we need to justify why the functions are continuous for all real numbers. So let's think about things that made us not continuous. Things that are not continuous, and it really goes back to domain. And so we're not continuous whenever we take the square root of a negative value, when we try to take a number and divide it by 0. Those are big things. 0 over 0, that means we've got to go and investigate just a little bit more to see what's going on. So let's look at x to the 2/3. Well, x to the 2/3, I'm not taking here, it's a cube root, not a square root, so that's okay. Nothing wrong with that. It's not a number over 0 or 0 over 0. So here, we're going to be fine with that. Y is continuous. Y is continuous at every real number. And a lot of times they'll call it every real number x. Okay, e to the x. Well, e is going to be a fixed value. Okay, and that continues on like pi would. And so if I take this real number here and I raise it to an x value, it's still going to be a real number. So here, this is really an exponential function. And so I can get rid of all that gobbledygook. So here we see that exponential functions are continuous everywhere. So just another thing to be aware of, right? And so part C, we've got 2 separate things to think of. Now here, this part, looking at the 2x, that is a linear function, and linear functions are continuous everywhere. So that's for us to remember. And then cosine. Even though negative cosine, that's going to be continuous everywhere as well. So again, we're going to have all of the y values. So again, cosine x is a continuous function. So notice these, it gets kind of redundant here, simply because all of these will work. Now, g of x is starting to become just a little bit interesting here, because we have a denominator to investigate. However, if I take x squared plus 1 and I set that equal to 0, well, I'm going to get plus or minus I. Well, plus or minus I, that's not real numbers, which is our real x and y that we want to talk about. So here, this one is still going to be continuous everywhere as well. So there's not a tremendous amount of places that we are discontinuous unless we just make them up. So here we're going to say continuous everywhere. Again, keep in mind that you're going to get those points of discontinuity when you're trying to divide by 0 or take the square root of a negative number, because those are things that we do not have in the real number system. Those are over in the complex. All right, so let's see if we can do example 4. Okay, if the function f is continuous and if f of x equals all that when x doesn't equal -2, then f at -2 equals what? Well, let's think about this in terms of limits. So in terms of limits, let's go back over here and say, well, the limit as x approaches, we said -2, because I'm kind of wanting to know an idea of what the actual value is. Well, x squared minus 4 over x plus 2, if I sub in that -2, I'm going to get 0 over 0. And that is what we called algebra magic. We had to go factor and do some canceling. So we can reevaluate our limit as x approaches -2. That's going to give me x plus 2 times x minus 2 all over x plus 2. Well, those x plus 2's will cancel, and so now I can reevaluate my limit as x approaches -2 of x minus 2, and that's going to give me -4. Now, let's think about what's going on here. This is showing me that my limit value here is at -4, and what we've canceled, that canceled part is what we set equal to 0. And we said that at x equals -2 is a whole. Well, the for sure value then of this, since we're not given any other information, is going to be -4. That's really what that value is approaching. If we were to graph this, keep in mind we really had the line x equals or x minus 2. And we know at -2, -4, we had an open circle, and then the rest of this, we just have a line. That's what we have found here. Every time we factor and cancel, we're cutting out a piece of that graph. All right, let's move on to the next one. Example 5 and 6, and these are our last two examples. You're wanting to know for what value can I make C so that I am continuous over all those real values. Now this really amounts to, and y'all, I'm cutting out a lot of the math stuff. All that this comes down to is looking at the limit as x approaches 3 from the left of g of x, and setting that equal, because you're forcing this to be continuous. You're saying, okay, I want to make sure this happens, so I've got to assume this limit will exist. And the only way that limit is going to exist is if these two things equal each other. Well, what am I going to do with that? Well, look, here's going to be all those x values that are less than 3 or to the left of 3. Here's all the values that are to the right of 3. So really this just amounts to plugging in 3 on each part and setting those equal to each other. So I'm going to have 3x plus 1, that's from the left, is going to be equal to, and I'm plugging in 3 again, so I'm going to get 9c. Oh, I put in x, y'all. Goodness gracious. Hang on. I've messed up. Not x. We're replacing x with 3. Sorry. So we're replacing that x with 3. So it's going to be 3c plus 1 equals, and the same thing over here. We're replacing the x, not the c. Goodness gracious. So that's going to be 9c minus 1. So now we're going to just solve this equation. So we can subtract 9 over, that's going to give me -6c, and I'm going to subtract 1 over equals -2. So divide both sides by -6. So the c value that must be there is +1/3. So again, here's this side is the theory of it, and there's the actual work. You will just substitute in your x value on top and bottom and set those little boogers equal to each other. All right, so let's look at example 6. For what values of x is h of x not continuous? Well, all right, so that means we've got to go through this definition. So, goodness gracious. Well, let's see. So, let's talk about being continuous. So, the first part, we want to know, and we're really discussing -2. So, does h at -2 exist? Well, h at -2 is going to be 3. So, my next part, does the limit as x approaches -2 from the left of the function, the function's not f, it's h, so h of x, let's see what that is. -2 from the left, so I'm plugging into this part, so that looks like that's going to be +4 minus 1, so that's going to give me -1, I believe, if I can do math. All right, and then what about on the other side? The limit as x approaches -2 from the right of h of x is going to be, well, -2 cubed, that's -8, plus 12 plus 3. So that looks like that's going to give me 7. Well, then the limit does not, oh my, so we've got a problem here. The limit does not exist, so the limit as x approaches -2 for h of x does not exist. Okay, so it looks like here we have found where we're not going to be continuous. We are not continuous at -2. And we just shown that because here the limit didn't exist, but we had a for sure value for it. So here the x values, or we could really, let's write a better conclusion. So we're going to say that h at x is not continuous at x equals 2, or -2. All right.